The SdSV 2021 challenge poses two main challenges. The first problem is that only a small amount of in-domain data is provided for training, and the second problem is that the trial consists of cross-language pairs, where the enrollment utterances are in Farsi, while the test utterances are in English. In order to solve these problems, we have submitted various systems trained with different combination of training sets. And some of our systems were trained using disentanglement techniques to remove the non-speaker information to help the system perform well on cross-language trials. Our submitted systems are based on the squeeze-on excitation ResNet architecture, which takes the MFCC features as input. The networks were trained using two types of objective functions. The first objective function is the combination of angular prototypical loss and the softmax loss. This objective aims to maximize only the speaker discriminability of the embedding vectors. The second objective function is the joint factor embedding, which have shown good performance in disentangling the effect of emotion and devices. The embedding network in the JFE framework is trained to maximize the speaker embedding vector's speaker discriminability while maximizing its uncertainty on the nuisance attributes. In our submissions, we have performed two types of JFE disentanglement. The first one is to disentangle the dataset dependent information, while the second one is to disentangle the language information. In our initial experiment, we have extracted a set of embedding vectors using an embedding network trained using only the voxel dataset. As shown in the TSNE plot, it can be seen that there exists a huge discrepancy between the dataset and the embedding space. This table shows the MinDCF performance of our submitted systems. As can be seen in System 2 and 3, which are trained using different JFE schemes, disentangling the language was found to be more effective than disentangling the dataset dependent information. Assuming from our previous experiment, this could be attributed to the amount of out-of-domain data used for domain disentangling JFE. From System 4 and 5, it can be seen that using voxel2, a very huge out-of-domain multilingual dataset, for pre-training the system and fine-tuning it with smaller amount of out-of-domain dataset was more effective. Although System 5 showed good performance, the best performance was achieved by System 6, which uses no out-of-domain dataset for fine-tuning the system. From our analysis, we could observe that there exists a huge domain mismatch between the datasets available for training the SdSV systems. Due to such mismatch, using out-of-domain dataset for training was found to be limiting the system's performance on the evaluation set. Therefore, in our future research, we will be focusing on effectively disentangling the domain information from the speaker embedding to allow the usage of more out-of-domain dataset for training.